time to discuss with Professor Tebaldini this morning. He will also review some of this part by another point of view that's useful for other engineers. So you remember, when I consider a limited slot, for example, this with some points that act as sources of signal, well, they just generate a spherical wavefront. It means that the wavefront is spherical and propagate with time in any direction with the same amplitude, so you have this. If you have the continuous antenna, the continuous means that the number of elements here are infinite, then you have this sort of emission, and you see exactly in the simulation the main lobe in which your energy is confined. So these are both coherent method. You know, if this is a black body, it will distribute the energy everywhere in the field in place. The radiation pattern is confined in an angle that is inversely proportional to the length of the slot. And here you have your problem, because now we are interested in the grating lobe. You see that there is much of the energy that goes here, but you see some other minor secondary lobes. One is this, one is this, one is this, one is this, one is this. So this is the first grating lobe, second, third, and fourth. These grating lobes should be, in theory, the same amplitude as the original grating lobe, unless the single antenna has some aperture, so they have some limited corner view. But unless it happens, these lobes are the same amplitude. And in this lobe, you can project here, you can put a sensor, and you can sense that the maximum of energy goes in this direction. If you change the wave length, now the grating lobes appear to move on the top of the, so they shift down or shift up, and so this means that a different color provide heat different part of the sensor, and you use them to construct a spectrum analyzer, to do multi-beam, and so on. Well, this is another case of a coherent sources. I don't have it on the PowerPoint. I have just taken out the simulation from Wikipedia. I hope that it works. I didn't test it, but maybe. Okay, so this is this one. Apart from, so this is how a laser works. It's a black body. Okay, you see, it emits a lot of energy. This is synchronized, so all the signals are emitted with the same time reference. When you have many of them, you need to have the synchronization. Okay. You see that they are perfectly synchronized since the phase is the same in all the positions. Okay, and this. Okay. So what you see in a laser is that you need a space synchronization. So you need to emit many sinusoids and having all the phase in the same position. This is space coherence. Laser has no time coherence. It means that the sinusoid changes the phase with the time, and this is not linear. It's very difficult to obtain time coherence in the microwave. It's pretty easy, but in the optical, it's not so easy. But it's enough to have a space coherence for having a collimated, strong source of energy. So here you see what is the scanning modes. So here I have taken many different. Of course, the scanning comes to the fact that you have a very directive beam and you want to observe the entire space. So the choice is that you have to move the beam in order to make a complete picture of the space, because you can only illuminate one small dot per time, and you generate a lot of movement. One way to scan, I didn't discuss about it, is to do a conical scan. So you scan in circle, this circle are smaller, 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 and then you have an entire. This is a very common, for example, for optical radiometer, because the scanning is very smooth. You don't have to make a sharp movement of the mechanics. So it's a very continuous, smooth motion. So it's pretty used, the conical scanning for microwaves. And this is another scanning. When you wanted to have a ground-penetrating radar, the way scanning is sort of human scanning, that you bring your device with yourself, and in vertical you have many sensors. So it's what you call a push broom, but here it's like a man that is pushing the sort of a push broom system. This is exactly how the system works out. These are the different scanning. So here you can have either a circular antenna or you can have a circular array. The difference between circular antenna and the array is that the array has many antennas. They don't move at all, but they can steer the beam in any direction. So in the circular array you have a great resolution, but you don't need any motion at all, and this means that you spare a lot of time. So the acquisition is much faster than ours. This is a meteorological radar. Meteorological radar, there is one also in this area. You can look it. If you go in the CML, Centro Meteorologico Lombardo, and write CML radar, okay, possibly you can find what is, and we can have just a demonstration because now it's raining, and you will see an application of the radar. So I just go on Google, okay, there is always a problem with the duplicate screen, so you see me, okay, just write CML. This is not active since years, just a few. You can have also a Telegram bot that provides you information about this. It's what you call now testing. So this is exactly a sort of snapshot in which you see the time. The time was a day in which the radar makes acquisition. You have two kinds of views. This is maybe the widest one. This is all northwest Italy. So this is the range of the radar. The radar is located in this position, more or less. So it means that here you see, what you see here is rain. Rain is moving, and for a Doppler effect that you will study, it's possible to measure the velocity of the rain and how much rain. So it means that this is a smooth rain, then you can have strong and even stronger. It means that if the rain is very strong, it reflects a lot of radar energy, and so you see very bright. It's like the surface, it's like the black body. You remember, the bigger the black body, the bigger the energy goes back to, or the energy is emitted to the, this is not emitted, of course, it's reflected, so the bigger the surface. So if the raindrop is very big, then you have much more surface, and you have it stronger, and you have also a measure of the velocity. So now we are in Milano, and now we are at, let us say, 50, 45, that is the last image. The last image is this, so it means that this is 30, 45. So more or less, now we are in Milano, and so there is some rain, but it's not really a big rain, so I can also forget my umbrella. Okay, that's good, and how you can get this sort of image, you get by this device. So you remember that the cover is huge because it's all North Italy, so it's hundreds of kilometers. You will see with Tebaldini how radar works and what you can expect by radar. So here you have a scanning that is just an antenna that is rotating inside the dome. The dome is that one that you use to protect the system, okay? Is this. Okay, this is the dome, okay? Well, this is pretty interesting. I hope that this works. It's a demonstration. Okay. This is how a radar scan works. Okay. You will see in the future. This is a radar. Why it has three antennas? It has the three antennas because one is transmitting and two are receiving, and you have two antennas Yes, this is a video. So I recorded. Usually I don't get the audio, so this is the first time I get the NDVI. So, and I did this campaign and this analysis. We have a spin-off that do this work. Look at the image. We are on the top of Mount Bre. There is a very good restaurant there if you want to go on summer. You have a beautiful position over Lugano. The kitchen is Switzerland, so it's not so good as ours, but the position is pretty good. You see, just you have the restaurant. And the radar image is pretty different because radar is measuring in range. So Baldini will show you everything about the radar. I want to anticipate. So for example, you are in this position, and so the scanning is circular. It means that you observe all this, and this is just recording based on the distance. So here again, the stronger the surface, the bigger the return. Of course, it's monochromatic, so the radar transmits only one wavelength, so you don't have the color. You can from some radar choose more than one. So here you have, for example, the lake. The lake is very smooth, so with the optical law of reflection, the signal is reflected at any other position, so you don't see the lake. The lake appears flat, you have also, of course, the shadow, and you have the town of Lugano. The range of this radar is 18 kilometers. It's not as wide as the one that goes in the air. Okay, and this is another interesting application with beamform. So here it's nice to see what you can do when you have a digital array here and you have a reflector. So this reflector is very big. It means that in the end the beam on the terrain is small, and it's what you get because you want a high resolution. So you want to have a very small beam. But now you want to point the small beam in different positions. So what you do? You just move the illumination from this to this to this, because if you reflect from here, the beam goes here, but if you reflect from here, the beam moves. And this is the same way your satellite television antenna put feeder in different way, and they just focus the signals that is coming from different satellite. So when you have, of course, all the reflector transmitting together, then the reflector is only a small part of the big surface, and if this part is small, the beam is large. So you understand. So large illumination on the reflector, small beam on the ground, small illumination on the reflector, very large beam on the ground. The rule is always that the angular aperture is always L divided by lambda. Lambda divided by L. This is a delta angle. So if L is large, the angle is small. If L is small, this length is small and the angle is big. So this is another application of beamforming, so of array. This is what, if you are interested, we are starting with Huawei. You know what is Huawei? It makes a telephone, but not only telephone. We are starting common activities with me about putting radar, but not this radar, new generation, the radar on vehicles. So they want to give us funding to study application of the future generation of radar put on the vehicles. This is a good activity for a thesis or for also a PhD doctor if you want. It's a very big interest because you see a radar can track many features simultaneously, and it can measure in real time the velocity of the feature. Real time means millisecond. This you can't do with optical system. You cannot have the measure instantaneous. You can do some measure, but there is a stray light, the light that goes in your eyes. Sometimes you have dark, sometimes you have shadow, sometimes you have fog. So the radar is the only device that ensure you 24-hour operation day and night. Okay. This is a very nice picture that I take one cloudy, one rainy day, just to show you different mechanism of reflection of the light. So this is clear reflection, but you have two different reflections. One is a diffused light, and the other is a specular reflection. Okay? What is the difference of diffused light and specular reflection? Diffused light means that you have a sort of surface that diffuses ray light, so the light means goes everywhere. And this means that if you illuminate from this position, you see the light from here, from here, from here, from here, from here. When you are in the specular reflection, the surface is very flat and the light goes exactly in one direction. Okay? You understand? So this is a mirror. If you look in the mirror look yourself, but if you look in the mirror's denting, you see another story that is exactly with the same law of optics. I know maybe you don't, I can just put out, sometimes I interrupt the slides observation. I have to make a trick, because if I switch off the PC, then I probably lose the synchronization. So my usual trick is to take the PowerPoint, okay, here, insert a slide, okay, put on the slide, you don't see, put on the slide a black, sentimento form black, okay, and then project the slide. Okay, it works. This is a black slide. So I can explain you how it happens. So let us consider that you have a smooth surface, then you apply the law of optics. So not sure the light goes in a precise direction that is governed by the law of reflection, that this incidence and transmitted angle are the same. What happens if the light hits a surface that is rough? So it's a rough surface, not a smooth surface, rough. So let us assume that it's as rough as having this discontinuity. So when you see the top of the surface, the light is here, and you expect that it is reflected in this way. When you see also the bottom, the light is here, and you expect the reflection going in this direction. So if this is a reflection, this is a wavefront. Okay? And if it is a wavefront, if the energy goes in this direction, then the phase is constant here. Otherwise, if the phase is not constant, you have a summation of different phases and you have zero. Okay? So you should have a constant phase here, but it's difficult to have a constant phase here because the light here makes one pass and the light here makes a longer pass. Okay? So it means that eventually here you have some phase, and eventually here you have some different phase. Of course, this depends on how much long is this with respect to this and with respect to the wavelength. So if you understand the principle, let us make a better picture in which we have only this, we have this, and this is a reflection, and we have the discontinuity, and this is a reflection. Okay? Then we have to evaluate orthogonal to the reflected wave, okay? Because the phase should be orthogonal. And orthogonal, this means that this angle is 90 degrees with respect to reflection. Remember that this is an incidence angle, that is also the reflected angle by the law of Snell, okay? And if this is an incidence angle, okay, this is the same angle, okay? This is the same as the incidence angle because they are opposite towards the vertex. I have to write it better. Okay. I can change the angle to emphasize the fact that this light goes here and this ray goes here. Okay. So this is incidence angle. Okay. This goes again here. So this is the same incidence angle. Okay, so basically this is the same incidence angle and this is the same incidence angle. Okay? Then you do what is the extra path that you have to consider due to the fact that the light goes here and goes here, okay? And you can use a trick So you can just double this discontinuity and you just put away that this is H, this is H. So if you double this discontinuity, you have this just reflecting in this position, okay? And what is the extra path of the light, okay? This is a reflected beam, this is other reflected beam, then you must consider the perpendicular. So, perpendicular to the wavelength, okay? Reflected, I must make a very good plot, otherwise I will not get the number, okay? This is a reflected, this is a reflected, and this is a reflected, okay. Okay. Then we go to this, and theta. I think that this is the way. From here I don't the extra path is this one. Let me wait a moment that I make it. Okay. Okay. So here I have a first ray that is incidence here and diverging with this angle. And this is the top ray, okay? The lower ray is incidence here and diverging with this angle, okay? In order to evaluate the extra path, I have to take orthogonal wavefront, okay? This means that when the ray has done this distance, this ray has done this distance. Okay, or let us say you can do the opposite. The extra path is this one. When the ray is so the extra path is exactly this distance minus this one. So the difference between the two. Okay, and just with okay, because it's here, the wavefront is orthogonal to the light, and so this is easy to compute. Because if this is H, and this is H, so this is 2H, and this is the incidence angle that is theta. Don't forget, I have try to reduce this. If it is vertical, it's very easy. This is emerging from here, and I have to compute this value. This is orthogonal, okay? So now it's easy for me to see, because this is emerging radius, okay? And this is the first radius. So the extra path is actually that you have to compute adding this one and this one, okay? Now you see. This one, because when you start the reflection, the other goes to the bottom. So the extra path is this length plus this length. This length is up to your orthogonal to the emerging waveform, okay? If you compute this length plus this length, it turns out that if you make a reflection, this length is actually this length, okay? In this case, the extra path is this one, okay? That's easy to compute, because if this is h, the elevation of the discontinuity, well, this is 2h, okay? That this is 2h, okay? This is the reflection angle, okay? It's the same as the incidence angle, so this is theta, okay? The extra path, I told you, is this one, okay? Because it's the sum of this that is equal to this and this. So the extra path is this, and this is length 2h cosinus of theta. Okay? So this is extra path. So if you put delta R, that is 2h cosinus of theta, and you impose that this is, well, if this is less than one wavelength, so if this side is less than one wavelength, so here you have less than one wavelength, we are more or less at very, very coherent. So any reflection goes there. So if this is much less than lambda, okay, I see lambda, it's a very big number, because if it is lambda, exactly you have lambda, you have exactly a coherent observation. Even if you put lambda alpha, you don't get a good number, because you have lambda alpha, you have two beam opposite, and so you have here one phase, and here you have the opposite phase. So you start having the same phase when you are at lambda 4. At lambda 4, it means that if you have here lambda 4, it's 1/4 of the wavelength. So this is lambda alpha. Okay, it means that one is here, the other is here, one is here, the other here, you can have opposite sign. If you have a distance that is within lambda 4, you see that you have a very correlated measure, much smaller than lambda 4. Okay? So this means that if the I multiplied by the cosinus of theta is much more than the lambda divided by 8, or let us say the I is much smaller than lambda divided by 8 multiplied by the cosinus of theta, you are in the limit of specular reflection. Okay? So if you want to have a mirror, you should have this relation. Okay? Obviously, this depends on the angle of theta, because if cosinus of theta goes to 0, this goes to infinity, so any reflection can be specular, but this is an extreme case. So if you put the cosinus of theta equals to 1, so the worst case could be when worst case is h equals 1 divided by 8, lambda divided by 8. So equal minus. If h, the discontinuity, is less than lambda 8, you are sure that the ray can go this direction, because the extra path is less than, let us say, a quarter of the wavelength. So you have two wavelengths that are shifted. These are shifted by less than a quarter of the wavelength, or these are shifted by the quarter of the wavelength, so it's not so much. And it's clear that if you want to do a mirror in optics, lambda should be between 400 and 700 millimeters. So you're speaking of much less than 200 micron. So 200 micron divided by 8 is a sort of 50 micron in optics. Okay. So if you have a surface that is less than 50 micron rough, then you really have a mirror. Okay. 50 micron is a very, very small number. Okay. In fact, only water, only particular polished metal appear to have a mirror. If it is H is much larger than 50 micron, then it means that it does not happen that the light goes in this direction, and if it does not go in this direction, then it goes everywhere. It has no preferable direction. So it means that when you have diffuse light, you have a surface much larger than 50 micron. Of course, on the asphalt you expect it, but also on this kind of surface you expect it, because this is they are not so flat. When you have instead this kind of precision, then you get the reflection. It's interesting to the fact that it applies to optics and to radar, but in microwave you are speaking of the wavelength of your telephone. The wavelength of your telephone is 25 centimeters. So if lambda is 25 centimeters, in microwave the specular happens when the elevation is the discontinuity is much less than 25 divided by 8, that is 3 centimeters. 3 centimeters is a sort of rough surface. Okay? So if you have a surface that is flatter than 3 centimeters, then you consider it to be flat. Okay? So what is flat in microwave can be, for example, oil spill. I told you that oil spill, you can distinguish between oil spill and the sea surface. Because usually the sea surface is not in the order of 3 centimeters, because you have some wind. And so the wind make a sort of wave. If the wave is the order of 3 centimeters, it is you have a reflection everywhere, and the sea surface is, let us say, gray. If the discontinuity is much lower than this, you have a flat surface, and the energy goes only there, and you see a blank surface. So you remember this, you understand why it happens down. So, if you understand this, you immediately understand why. Okay, you sometimes see a reflection, specular reflection. Sometimes you don't see the specular reflection, because the water it's smooth within a very small fraction of micron. And when you have water, you have the specular reflection. Otherwise, you have diffuse reflection. But this is the same case that you can get. So, how do you interpret that sort of spherical, circular dot that you have? This is just a picture that I make with my phone in a lake. Okay, how do you interpret these spherical dots? Okay, you see this circle. You have many circles. On the right, you have a zoom of the card in which you have a circle. Okay. What's happening in that circle?
Sunshine.
You have reflection of sun, but why in some position you have circle and in other position you don't have? Okay. So this means that, just to make an example, if the surface is soft and the sun is here, I have a spherical dot only if my camera is in this position. If I change the surface position, then immediately all the energy reflected goes in another way. But why it is very strong? It is simple why it is very strong, because when you have a reflection different from the scatterer, so when you have scattering here you have the light. So I can say here you have the light, but you have the light diffused everywhere. When you have the specular reflection, Then you have a quantity of energy that, so what is the difference between a specular reflection and the light? We can put it here just in one piece of the blackboard. So the difference is between a coherent source and a black body. So the black body is like a specular reflection. You are spreading light in every part of the space. Of course, if you have the sea, you're not going energy down, but in any part of the space. So theoretically, this angle is a spherical angle, and you remember that the spherical angle is 2 pi, okay? It's 4 pi. 4 pi r squared divided by r squared, it's 4 pi, okay? So it's 4 pi as the total spherical angle, okay? When you have a smooth surface, this is like a coherent antenna. So let us assume that the smooth fossil is very, very smooth. So it's 1 centimeter by 1 centimeter, but then it means that you have an angular aperture that is much smaller. So if you want to compute the spherical angle, you just have to multiply the size of this, that is lambda divided by L, and the aperture in the other direction, that is again lambda divided by L, okay? So lambda divided by L and lambda divided by L is, well, lambda, let us say that is 700 nanometer, for example, so is 0.7 times micrometer, 10 minus square, and you divide by L, that is 1, 10 minus 2, and then you put the square power, okay? So this means that is 10 minus square, 6, 10 minus 2 is 10 minus 4. This is very close to 1. So it is in the order of 10 minus 8. Okay? So it means that from 4 pi to 10 minus 8, you have 8 times approximately 4 pi is 12. So you have 7 order of magnitude. 7 is 10 million, okay? So this means that if this wave is specular is just 1 centimeter, you have 10 million energy that hits your receiver with respect to the energy that you get from this point. Now you understand why it's impossible to have a linear behavior, because you have 10 million energy. If you have 10 million energy and the point spread is this, what is this? This is the length. So it's a point spread of the length. And since you are using a circular lens, you have a circular point spread. But as this point spread is 10 million and your dynamic fixed here, you just see a contour of the point spread. So you see a circle because your length is circular. Okay? If you have a square antenna, you will see a square, because approximately the point spread very down is more anisotropic than a perfect circular antenna. So this is saturating, possibly it can also create a danger to the CCD, because it's a lot of energy that hit a very small pixel, unless you design a proper CCD, of course. This is another sort of analysis. What happens in the black, okay? Here in the black, I don't know what is this, but here in the black, you have this sort of behavior. So you see, you have a grainy behavior. How you have a grainy? Because it is quantized, you don't have many photons. Sometimes you have 3 photons, sometimes you have 2, sometimes 1, sometimes 5. So you perceive a variation of photon like a sort of noise. That is a random fluctuation of the amplitude. And you see also these photons are different colors, because since they are quantized, sometimes you have more blue photons than red photons and so on. This means that you have also a degradation of the quantity of color. And by the way, you have shadow. This is very interesting, this sort of color, okay? When you emit the light with the sun, you expect that the profile, the power spectrum of the sun is as from Planck law. Actually, there is slight difference from Planck law, because atmosphere is a sort of a filter, and it's not a filter that is constant in all the frequency, but it's very similar to a Planck law, okay? So you have this profile of energy, this is the visible, of course. When you see another source, for example, this source of light, well, a LED, for example, the emission is very different. Okay, so it means that if you record this, you have more energy down to the red, and so sometimes more energy down to the violet. So if you have different sources of light, you see that the color changes. Okay. Actually, your eyes don't see a change of the color because your brain is very clever and do an automatic calibration. So you understand, for example, that by your experience this should be white. The eyes do not provide the same power spectrum, but let us say the brain recalibrates this in order to put this in bright. Okay, this in your camera is called color calibration. Okay, sometimes it's done automatically, sometimes it's done manual. So if you are making a picture with some light, some fluorescent or some artificial light, and you see an average different color, it means that your camera is not a good color correction, that is color calibration. That is a sort of calibration. This is another way you can have a calibration. So sometimes when you have a representation of the signal, you have a sort of distortion. This happens very often when you use your phone camera, particularly when you are very close to the camera. All the selfies are distorted in this way that the nose appears to be very big and the other part of the face appears to be small. But of course, if you know everything about your camera, your position, you can have a geometric calibration and put the point exactly in the position where they are. This is something that you have to do, and in order to have to do, you must know where the points are in the space. So with only one image is impossible, but with two images, it's possible to have the 3D exactly in the right. Sometimes you have a 3D in a very simpler way, so you can just put structure light, and by looking at how the shapes, so how the light, the reflection, as deformation in the shape, your brain reconstructs the 3D, and so you have only one image and you have the 3D that is very interesting in the play, because otherwise you should have two cameras to have the 3D. Here is another example, okay? You exactly understand the 3D if you look at the contour of the light that makes. So from shading, you have a lot of information, usually in optics and also in SAR, that you eventually exploit for new applications. That is very interesting. So this is the emission of the moon. For example, this is a reflection of the light, of the sunlight. You see spot, but in the average the moon is very constant, and it's a known temperature, so that people use the moon to calibrate for a particular temperature. Okay, and here we see back the first images. You remember the images we studied, and I told you that in the visible, when the sun hits vegetation reflects a lot in the infrared. Because the other light is very useful for the chlorophyll and so for the photosynthesis, but the infrared is not useful, it's too long wavelength. So they have most of a reflection, total reflection is the infrared. In fact, the vegetation is here white. And exactly if you measure the quantity of light at 700 nanometer, you have the index of vegetation, because you see here is also vegetation. No one is reflecting so much exactly in that part. And if you look at reflectance, if you look not in reflectance, but here it's in radiance, so this is the natural color of any object. And here you see that the intensity tells you the temperature, okay? So the higher intensity is a higher temperature, and this is exactly Stefan Boltzmann equation. Of course, here you see only some wavelengths, and they should be in the infrared, because most of the energy you see a human body at 23 degrees with a peak of 9 micrometer. 9 micrometer is 10 times higher wavelengths than the sun, and this is really what is called far infrared. So you need particular instruments. This is another example. Then you see a clear mark effect of the vegetation also on the grass. You see where it is a grass is white, where it is a green becomes white, much whiter than you will see in optic. In optic you will see green, but green is not brighter than other. But in infrared, of course. And these are the two missions we were discussing about the last lessons, the two hyperspectral. So I told you an hyperspectral, usually in your eyes you can observe only the visible, okay? So you have this sort of 7 color, or let us say 10 color. But if you stand in the short infrared or in the long infrared, and then you have a lot of capability of doing more application, of observing more, okay? And this is what will be the observation of hyperspectral. What you do, for example, if you look in the wavelength domain, so also including the infrared, and you see what is the reflectance with respect to the frequency, this is soil, this is wavelength, and this is vegetation. So each material has a different, let us say, spectral signature, okay? In the visible, maybe you don't see so much because you have only a very small spot of this. So you observe only a small part. So sometimes you are not able by your eyes to distinguish different things. For example, you know, infrared is used for money, okay, for the cash, to understand if they are false or light. Because if you have some infrared, you have some more deep extension in the spectrum. But if you extend it to a wide spectrum, then you will see something that with your eyes will never see. And this is called, well, this is material, for example. You see the difference between tree, fabric, paint, and grass. You see completely different spectral shape. And it's funny to see that there is not big differences in the visible, but the difference comes in the infrared or close to the visible. So I say if you have an ice that extends, so an hyperspectral ice, you will see much different stories than what you see. For example, this is Aster. Okay, Aster is a sort of this hyperspectral system that is mounted on an airplane. This is a minefield in Chile. It's a famous minefield for copper, but you have a lot of more information. Each color corresponds to a different crystal, so to a different mineral. And this is what you see with your eyes. Okay? And this is what you see with an hyperspectral observation. So you have because the hyperspectral enter in the atomic and in the molecular composition, and so have all different signature, and you can make, this is an example, and you can make a database of signature. For example, this is different name, amorphous icon, hematite, hematite medium grain, graphite, jarosite, all the minerals have a different signature because all this is a signature of the quartz, the spectral signature, and look, I'm looking from 6 nanometer till 14 nanometer. So here again, 0.5 micrometer to 3 micrometer. So this is the entire in the infrared. It's not none in the visible, and this short part is visible, and this is entire in the short and long infrared. So you see, for example, calcite has a different behavior according to some presence of different molecules, so different molecular structure has a different behavior in the 2 micrometer, so the near infrared. And then you can measure this and can do a classification and see the color image left. It's not what you get when you have your wide observation. Is that for each pixel you take all the spectral bandwidth. So for each of the pixels you have an entire spectrum. You do a matching with respect to the signatures that you expect, and you have a classification. So this is just saying each pixel which material is that. So immediately you pass over an area and you know what crystal, what minerals are there, and this is a very, very powerful application you cannot do with optical observation. You need this is the same, for example, application with other different concrete, dust, cement, so different application. This is a panchromatic image. And the point is that what is the point? Is that, of course, in the visible you have a lot of energy. In the infrared you have much less energy. That is a major point. So you don't have so high energy. And you know that energy comes, as for Planck, as a ratio between, let us say, the power spectrum and the area that you are looking. So if your cross area is bigger, you get more energy. So this means that if you have a weak energy because the emission is infrared, then you must increase energy by looking at a bigger area, a bigger black body area. And looking at bigger black body area means you lose the resolution. Okay? In the end, you recover more energy by observing a bigger resolution set, so you lose the resolution. So there is a trick that is called pan sharpening, that you say, of course, if you put all together, so if you do in the, what is the monochromatic, that is putting all together the wavelength, so you see only one color, but a very high resolution. Then you can decompose into many colors, okay? But now you lose the resolution, because a single color, it's a small part of energy, so big resolution cell. So the idea is that you put together the high resolution cell that you get from the monochromatic, and the color that you do a fusion between a color and a high resolution monochromatic image. This is called pan sharpening. So you're saying that here, for example, in this pixel, the dominant color is this, but the resolution is provided by the gray image. So pan sharpening is a very powerful technique that tries to improve resolution, even if color resolution is always limited. Okay, and this is a sort of pan sharpening image. I don't know what is this. Ah, no, this is okay. This is not okay. What is a pan sharp? You see that sometimes you have a sort of spot that goes beyond, because of course here you see you have some false border, because it's like you go in the edge and you write in the edge because your resolution is very dark, but the result is a very pretty good result. There is a lot of signal processing and classifications that you can do with these images. Our course, it's not enough, of course, to provide this, but you can understand what you can get. Okay, here, for example, you see the difference between phytoplankton and chlorophyll by looking at here again the spectral observation, and here you see, for example, how the NDVI changes with the quality of the vegetation. If the vegetation is very good, is very healthy, the NDVI goes to a very, let us say, blue level. Okay, so blue high NDVI, so good vegetation. Red, the vegetation, or it is not vegetation, or it is vegetation, it has a lot of problems. So it's not emitting much energy, so there is not many activity there ongoing on photosynthesis. Okay. Here another example, normalized digital elevation index. You see in false color, infrared, or in red. In red is just the NDVI. So you see that NDVI is circular because this is a circular irrigation in the desert. So where you have the irrigation, you have the vegetation. We don't have irrigation, or don't have effective vegetation. You don't have this is, you know, because this is your homework. By the way, Tebaldini today or tomorrow will send to you. Maybe he has already done. We were discussing this morning, and this is the way how a system is done. So you cannot have vegetation in, you cannot have imaging is a panchromatic in the visible near infrared and is a shortwave infrared with only one CCD. And so you remember that this is a sort of telescopes that do a lot of amplification with lenses. Here you have one CCD, panchromatic, one CCD, and here you see a grating. This is what you have to design. You remember that the grate is length, the band, and band a different color, and different color with a different column of the CCD, and you have the hyperspectral image in this domain, and this is, you see, here is the infrared that is not visible. You have only one color, because here you cannot have the possibility of distinguish color, otherwise you will not have energy. So you have only one color for the very wide bandwidth to recover some energy. This is MODIS, is one of the best spectral radiometers. So you are measuring the emission, but you are measuring the emission with a color. So for example, you see the level of heat, the color here, it's classically the temperature of the sea surface. And it's very important because when the sea surface temperature is very hot, the sea is going to be very high. And there is a very big event ongoing. This is El Niño. El Niño is famous. Someone of you knows what is El Niño. Okay, El Niño is a sort of, let us say, a big current that creates typhoons and cyclones. So it's creating a lot of problems because it's an anomalous increase of temperature in this part, in this equatorial part of the ocean, and this increase cause winds, cause a lot of devastation, and there are no way actually to predict the Niño, and this is some works are ongoing by this radiometer. So this is how a spectral radiometer works, so how the bands are seen. So you see there are many absorption bands, so many bands in which the atmosphere does not emit at all because it is water vapor, so water vapor takes all the energy, so you don't have energy. This is an average spectrum. You see, when you have high power, the band could be very small. When you have low power, the bands are bigger because you need to recover energy. And this is a sort of application of the way water vapor. Water vapor is circulation of let us say, of the wind. Okay, and this is very important for weather forecast. Okay, so weather forecast is a service that is everywhere, and you see how circulation is made in vortex. So you have really a lot of vortex, a lot of big vortexes, small vortexes, smaller vortex, and very small one. And this is the ones that carry you eventually storm, typhoon, or just the rain of this. So understanding every minute the circulation is something that is a very important thing we are trying to do with radar, because it's not possible to do with this instrument. So you don't have a good analysis at high resolution on the land. On the sea you have at high resolution on the land. Here is temperature, so I want to show you here this image, because when you look in the infrared, they call also thermal infrared. Why thermal? Because you see what is burning, okay? Basically, you see all the foci or the central, whatever you have burning. Here, for example, is the fire here in Central America, and here is the distribution of the fire in the water. Of course, this is not an optical image, it's a thermal infrared image. So it's sensible to all the position when the fire comes out. So if you know you want to monitor the fire, you go on MODIS, and in real time you have this. Here an example of an aster image that is again a multispectral, in which you can combine different bands. For example, if you combine the bandwidth 3 to 1, you have this, and if you select a different combination, so instead of 3 to 1, you make a bandwidth 8 to 1, you have this. Here you have more the effect of the smoke, you have less effect of the smoke, and you have more contrast on the burnt area and the good area. So sometimes you have to put the good combination of band just to observe something and to cancel some other. Okay, and this, for example, is all the sensors. There are a lot of satellite every let us say every hour, every time on your head, and they are moving, and most of all provide the data that you can acquire. You can get even for free in most of the cases. All NASA satellite and many of the European satellites are for free, and you say, but what is my satellite? Well, this depends upon what you want to measure. Here you have a space resolution, maybe you want a resolution of 1 meter, usually you pay. So for the high space resolution Iconos, for example, QuickBird are not for free, and you pay a lot of money. But let's say starting from 10 resolution to 1 kilometer resolution, you have many sensors, and then you pass say how many spectral band. Okay, for example, on QuickBird you have only 1 band, so you have a monochromatic photo, and that's all. Okay. On other images, for example, on Iconos, maybe you have 8 band. Okay. Of course, some applications need more band. So this is Hyperion, for example. Hyperion is cancelled because Hyperion is not working since 1 year, but until last year for 20 years, now they are doing again, and this will be Prisma will do the same stuff of Hyperion. Has a lot of band. It's the one that have more bandwidth, but it has less resolution. Okay. So sometimes it's a trade-off. If you want resolution, you need some satellite, but if you are interested for a specific band to observe a specific behavior, I will do a couple of exercises just to use your PC. You download the data from the web, and you combine the band and use the feature. I will do a practice exercise in the future. Tebaldini has allocated me a couple of exercitations, and this is AVRX, another advanced visible infrared system. So for spectral signatures, this is sort of application, hyperspectral classification, and hypercube of 126 band. You see very different results from what you see on the sea. And this is, for example, the ocean color. And yeah, you have, for example, the content of chlorophyll. And the content of chlorophyll, this is an image that I put in 2014, but you can do in every day. Because, this satellite, this is a service that is marinecopernicus.eu. So I suggest you to go and to log on marinecopernicus.eu. You can do an experiment just to show you what is the powerful of Copernicus system. So this is a radar. See. So by the way, if you see, our radar says that okay, this was at 420, okay, 440, 450, okay, then you can go without your umbrella. More or less it's the same, okay. At least there is some residual in Milano, but most of the cloud is good. Marine Copernicus Marine Environment Service. Well, all these services that you find here are for free. Okay, so if you want to have the ocean product data, here you have just a browser, and when you load, you find, of course, you must find some criterion. For example, you are interested in the Mediterranean Sea, and you see some map that is appearing, and there is a chart, but you remember that everything is free. So what you put in the chart and you download is just if you want to download on the PC. This is, for example, Med-Sea analysis forecast, and of course this is a different type of analysis. This is a temperature, okay, and this is 2015. So because I don't put any filter, I filter this, but I can say, no, I don't want a filter starting from 1992. I want a filter starting from, let us say, 1992, 1997, not even 1997. Well, okay, I have some problem with the window. 1990, okay, 1911, 1916, okay, and 1916 August, and then you choose a date, and then you go, okay, or and product with that level, and then you get immediately the product. This should be regional domain. I have already set the parameter. If you want salinity, for example, or you wanted to have the wind, is another observation, and of course, no, you don't have any. So you don't have windows Mediterranean. Of course, it's not everything everywhere. So for sure in the Mediterranean you have the temperature, but maybe in the global ocean you can have some parameter about the wind. Okay, so this is a global parameter, global observation, and then you can download this, you can export the result to find matching criterion. Okay, yeah, the resolution that is 1 degree by 1 degree. 1 degree means 1 degree in the Earth. You know that the entire turn of the Earth is well, the radius is 6,000 kilometers, so it's 40,000 kilometers. Okay, for 40 million meters. 40 million meters divided by 360, and this is 1 degree. Okay, so this is the resolutions that you can get. So these are very global map, and you can get from. But we will do an exercise of this is Copernicus. That is the European program that provide any kind of service. It's not only marine. You have also other services, and this. So for today, I finished a little earlier because I just conclude. Let's say this, okay. I just conclude with this my observation, with these potentials, and I recommend to follow all the radar course, because I see not only for research but also for maybe your thesis or for the works that you do in future, there are a big opportunity to use the radar, and Tebaldini is one of the best in the world, not only in Italy. Okay, Italy, you know, radar in Europe is very strong. We are stronger than any other part of the world. Radar is a long-going history that started from Hertz, that started from Marconi, that all European countries. In fact, the bigger radar manufacturers are in Italy, that is Thales Alenia Space in Italy. For big, let us say, spaceborne radars, there are only 2 manufacturers in Europe, and they are also exporting to Taiwan and to other parts of the world. One is let us say, in Germany, okay, and this was Dornier, now it's called Airbus, and the other is in Rome and in Thales Alenia Space Italy. So they are 2 big manufacturers when you want to have a spaceborne radar. Then there are some emerging new, but these are the best in the world. So it's something that in Italy we know very well, not only how to build, but also to operate. Next week I will go in China, where we have also our activities, because also in China are interested to European manufacturers. So thank you for attending this course, but this part of the course. But please remain for the other parts that are, you will enjoy it and you will learn a lot of interesting parts. Okay, and remember the homework. Okay, you have 1 month.